Hey class, Mr. Bean here for Honors Physics. By request, some people want me to give some hints on Lab 41, the circular motion sims, and so we'll go ahead and do that. So this is simulation number 2 here, and it's called OSNAP, and here we have this thing going around in a circle here. So currently this thing is going 5 revolutions, right? 5 revolutions in 1 minute. So that's how fast it's going at this time. All right, so the question is asking us is, take a look here. Object has a mass of 875 grams. So we'll go ahead and put in here mass is equal to 0.847, like so, 0.847 kilograms. Okay, got to be in kilograms. The radius, we'll have to measure the radius. Okay, and the breaking strength of the ball, so the tension at which the string will break, is 2.19 newtons. Okay, so it says here, what is the speed at which it snaps and what is the corresponding RPMs? Okay, so that's what we need to find here is the speed and the RPMs. All right, so let's go ahead and hide the question here. And first things first is we can get the radius. So I'm gonna go ahead and kind of see where it goes. So let's see. So about right, yeah, I'm gonna say about right here. So each one of these, so this is about 9 point, so each one of these is zero point 0.1 meters. So it's going to be about, in my case, it's 9.5 meters, or excuse me, uh, 0.95 meters. So we're going to be 0.95 meters, okay, because this is 1 meter to here, 2, so zero point 0.1 point, yeah, so 0.95 meters, okay. All right, so let's get the V first. So let's figure out, so centripetal force, right? So the force of tension is right here, and it's going to equal m v squared over r, like so, mv squared over r. Okay, and so we have the mass, we have the radius, and we have tension. So we need to get V. So from here, I'm going to rearrange the equation, right? So it kind of looks like this here. So here's velocity, and velocity is going to be, in this case, force of tension is here, right? Times R, right? Times R divided by M. Okay, check the math here. So this will get us V. Okay, now, so this would be step 1. Okay, now step 2 is going to be RPMs. Okay, it's the RPMs. It's basically omega. Well, it's kind of angular speed. So we'll say angular speed. Okay, angular speed. All right. So the relationship is V is equal to omega times R. Now remember, this omega is radians per second. Okay, so what we have to know is that 360 degrees is equal to 1 revolution, which we know, 1 revolution. And that's going to equal 2 pi radians. Okay, 2 pi radians. We have to make use of this. And we also know that 60 seconds, right? 60 seconds is equal to 1 minute. All right, so we have to use this fact here. All right, so first of all, let's go ahead and solve for omega. So omega is just going to be V over R, okay? And we will get some answer here, okay? We'll get some answer, okay? We get some answer. Now, we're going to use the factor label method. Okay. Once we get this answer here, we have this is going to be in radians per second. So we have to get it into RPMs. So the first thing that we're going to do here is we have to make use of this situation here. So it's going to be revolution. It's going to be radians per second. Okay. This unit's up here, radians per second. Okay. So that means that we have to have 2 pi radians here. So there's 2 pi radians here, and this will be 1 revolution here. Okay, and then we have to times it by, so the units for this answer is going to be radians per second, like that. Okay, and then so we have radians per second. So we're going to have here 60 seconds is right here, and this will be 1 minute. All right, and then that gives us RPMs. All right, go and give that a shot, and we'll come back with simulation number 3. All right, class, this is simulation 3. It's called finding a speed of a satellite. So go and take a look here at this here. So we have the satellite that's going around in a circle here. And the first thing we need to be able to do, they have some things here where, first thing I want to do is go ahead and start the timer. So this is going to get us the time it takes to go all the way around in hours. So while this is going here, we can take a look at this information here. It says the planet's radius is the factor times radius. Okay, so let's show the question here. R is 1.9 and is Titan. 1.9. So we'll go back over here, and so it's Titan. Okay, that's our planet or our moon that we got here. And so the factor is 1.9. So that means it's going to be 1.9 here. And we need the radius of Titan. So let's go ahead and do this first here. As soon as I make one revolution, I'm going to hit pause or hit stop. Okay, and boom. All right, good. So the time, okay, so the period is 13.22 hours. Okay, but we do need to get this into seconds. Okay, so that's going to equal. There are 3,600 seconds in 1 hour. Okay, so you're going to have to multiply this by 360 seconds here, and this will get us the answer in seconds. We have to do that. All right, so Titan. So got to find Titan here. So here's a Titan here. Looks like the radius is 2.575000. Okay, so we're going to take it times it by. Now I would just do 2.5 and just do E, just do an exponent here. So where's Neptune? Here's Titan here. So 1, 2, 3, 4, 5, 6. So E to the 6, 2.5 E to the 6. That's what I would do here. Okay, and that's the planet's radius. So I would do this calculation first. Now this is actually in meters, so we don't need to worry about this. So multiply this, and that should go right here. Okay, that should go right here. Now the altitude, okay, show the question here. So the satellite is an altitude of 2612 kilometers. Okay, so 2612 kilometers, and we want to go to meters, so just add 3 more zeros to that. So it'd be 2612000. Now if we need to, we can go ahead and maybe make this in scientific notation. So 1, 2, 3, 4, 5, 6. So we'll just say 2.6 E to the 6. Okay. All right. Meters. Okay. So we have the radius in meters and we have the altitude in meters. So what we're going to do now is add them together and we'll get the orbital radius R. So make sure we're going to add the planet's radius and altitude, and that should go here. Okay, and we want to get T in seconds, okay, by doing that, okay, and then simply speed is equal to distance divided by time, okay. So what is the distance? Is the circumference, which is 2 pi r, okay, and divided by the period, okay. Now, so just do that calculation here, and that'll be the speed, okay. And so if we go enter answers, it's going to be your name, the speed, and make sure we have the period in hours. All right, we'll go ahead and get ready to do simulation number 4. All right, so simulation number 4 is the ice bucket challenge. Okay, so in this problem here, they're asking us, so what's the minimum speed that this can go in a circle so water does not come out here, or water doesn't fall out, and 2, what's the maximum speed in which the string will not break at the bottom? Okay, so we have to consider two cases here. Okay, the top and the bottom region. Okay, so given is 9.8 meters per second squared. Okay, the mass of the bucket is given here. That should go there. The radius is also given to us, and the strength of the rope, which would be tension. In this case, is 191 newtons. All right. So strategy: divide the problem into two parts, top and bottom. So the top region is to keep the water in the bucket, the centripetal acceleration must be greater than 9.8 meters per second squared. Therefore, the minimum speed can be used by using this equation right here. Okay. Now, and then plug 9.8 in for centripetal acceleration. Here's v, and here's the radius. Simply solve for v. Now, this is one way to do it. Now, in class, we were talking about the normal force, right? Plus mg was equal to m v squared over r. Okay, and this was at the top. Now we said that what happens is that when normal force is 0, water is going to fall out. Okay, so when this is 0, we can see the m's cancel out here, right? So what we have here now is we have v squared is equal to gr, like so. Okay, and therefore v is equal to the square root of gr. Okay, and that's what this is over here. So this equation are the same. Okay, same thing. All right, so that should get us the minimum speed needed to go in a circle so water does not fall out of the bucket. Okay, bottom region. Okay, the force of tension cannot exceed the value given for tension. So we want to use this equation here to find V. So simply, we have the force of tension here, right, equals, so here we have M, okay, so we have M here, this is V squared over R plus G. Okay, so we have all the values we need, and so if I was going to do this problem here, we could have, this is the force of tension divided by M is equal to V squared R plus G, right? Okay. Then if I needed to, from here, we should be able to solve for V. So you get V, and this should be V maximum, the maximum speed in which you can have this bucket going so the string does not break. All right, so when you hit end, you're going to put your name, the minimum speed, and the maximum speed. All right, we'll hit pause here. All right, last problem here is going to be the normal force on a spinning space station. So go ahead and hit begin here. And here we have the space station, which is going in a circle. And we're going to try to simulate artificial gravity. Okay, and so we'll go ahead and kind of read this here. And so you need to create the normal force on this rotating space station so that create a normal force for a 78.9 occupant on the ship will match the normal force they would experience on a planet with the same gravitational field strength, or G, okay, meters per second squared. Okay, so 5.8 newtons per kilogram is the same thing as meters per second squared. All right, so first things first here, so what's the mass? So in my particular case, the mass is 78.9 kilograms. And what's the G on this planet? Here is 5.8. So we have your 5.8 newtons per kilogram, okay, which is the same thing as meters per second. Okay, how do I know that? Okay, so newtons over kilogram. Okay, here's kilogram. Okay, but newtons, okay, so here I'm going to put 1 over kilograms here. And newtons is basically kilograms meters over second squared. So the kilograms cancel out, and we just have meters per second squared, which is what we know. Okay, now the radius, okay, so in this particular problem here, the radius is given to us as right up here. So it's 516 meters. So here's 516 meters. Okay, so the strategy, you need to calculate the normal force on the given planet then need to calculate the rotational speed such that the artificial gravity can be created on the space station to simulate the normal force on the planet. So first things first, let's go ahead and do Fn is equal to mg. Okay, so let's just take a quick look over here. View from inside the station. Okay, so what is the normal force over here? So it looks like the normal force, so this person is, here's his weight here, looks like it's 3 newtons. Okay, all right, so 3 newtons is over here. Okay, so, or, pause. All right. So first is calculate the normal force. So the person's mass is 78.9 kilograms, and the normal force is 5.8. Excuse me, acceleration due to gravity is 5.8. So we do this part here first. Okay. Now, here it says 3 newtons. Okay, that's what it is currently on the space station. So we have to speed the space station up so this answer here, whatever shows up here, will match this answer here. Okay, so once we get Fn, that would go here. So from here, we need to get V. Okay, what's V? So from here, we need to solve for V. So V equals something. Okay, so we have V. Now the third factor is we're going to use this situation here. V is equal to, remember omega again? Omega times R. Okay, so here is my omega here. Okay, and we're going to have here V over R. Okay, now I got to be careful now. Okay, because this omega is really has a units of radians per second, right? It has radians per second. So we have to do factor label method. Okay, so we're going to have to do 2 pi radians, right? 2 pi radians right here, and 2 pi radians, and we're going to have here 1 revolution. Okay, now the answer, they want us to put the answer in rotations per hour. So this is revolution rotations. That's fine there, but this is radians per second. So we have to figure out, okay, we have to convert this to hours. So radians per second. So we know that there are 3,600 seconds in 1 hour. Okay, so I would do this multiplication here, and I would get an answer here, and that should be my answer. All right, that concludes it. Any help, please let me know.